Hi, today I want to talk about the vision transformer and how we applied it to mel-spectrograms for audio classification. Let's start with having a look at audio classification. There are basically two ways. With one, you can take the audio or the raw audio and directly apply raw audio models on it. In the other case, you take raw audio streams or raw audio files, which are sequences of measurements, and transform them to mel-spectrograms, or in other words, a spectral power density map. Then you can interpret or take those spectrograms and apply image models on this, especially in the context of deep neural networks. There are some very prominent models which perform very well by taking spectrograms as images for such models. We followed this course and applied the vision transformer by Dozovitsky Alexei et al. From the paper on images worth 16 times 16 words. And in the very left, you see how they apply the transformer, which is a model that takes sequences to work on images. You see on the very left, they take an image, or in our case, a spectrogram, and slice it down in squared patches. And following the ordering you see here, but you can take a lot of more patches and slice them in smaller or bigger, just as you like, and how it suits to your problem and your data set. We further investigated in the application of a model which we call the vertical vision transformer. It's practically the same model, but the patching or the way we sliced the data is different. We wanted to have a look at all the mel-spectrograms at the same time while following the temporal axis or the temporal dimension. For further details, please have a look in our paper. We compared those to very strong baselines, the convolutional baseline and a subspectral classifier. Those are models or neural models, deep learning models, which work on the spectrogram as well by utilizing image or technique from the image recognition or image classification community. After very intense hyperparameter tuning or finding for each individual model, this is the scores we came up with. So long story short, the vision transformer performed very well on the primate dataset, not so much on the coughing dataset, which we found a very overall bad performance, but still we achieved better performance in the development dataset in comparison to a very strong baseline given by Compari. My time is up. Thank you. Let's have a closer look on the observations we made by applying the vision transformer on audio classification tasks. First of all, here you see the pipeline we implemented. We first have the raw voice or primate recording in this case. After that, we transformed the total data sets, both on which we had looked, namely CSS and PRS, and transformed them to a mel-spectrogram. We then applied a mel-audio augmentation, but we did this on the flight. So you can think of a very vertical line between those three images, and the mel-augmentation lies within the model training process. So this image is not quite correct. Here you see an overview of the augmentation techniques we used. We also did a hyperparameter search on which are the best parameters per dataset and per model. So this was a very wide and very extensive, let's say, hyperparameter search. After that, we found the special, let's say, we made these special observations. First of all, on the middle of the screen, you see a confusion matrix on which you can read that we have a notable mix up of background noises, which is class 0, and chimpanzees, which is class 1. So we think there's further pre-processing necessary to kind of find the outlier on the very closely related voice recordings. you could maybe take the model and apply it on data sets where you have an indication for a strong background noise. I guess urban 8K and something like this should be very good data sets for application. But the VIT or the vision transformer takes a very long time to train, and you need on a Titan XP graphic card, you'll need about weeks, I guess, to do stuff like that. Let's have a look on the parameter importance we found during our testing and our hyperparameter search. First of all, we found that data augmentation or the models are very sensitive to the augmentation apply chance. So it very strongly depends on which augmentation you use on which data set in comparison to which model you use. On the other hand, the learning rate was quite let's say insensitive parameter, and you have to figure this out very well. So we would really, and this is not a parameter you can guess very well, like the architecture or something like this. You see the number of heads or the embedding size doesn't make a lot of a difference here within the model. But if you choose the wrong learning rate, which are often given for specific data sets, you can make, let's say, a big error choosing the wrong one. I guess those are parameters and observations we have to deep in more in we have to go more into detail on those observations, and we think that something like attention rollout would be the right measurement or the right tool to do something like this. That's from me. Thank you.
Okay, thanks a lot. Are there any questions to Steffen?
Oh, there's a very long one in the chat, but I guess I can answer that later.
Okay. So thanks a lot, Steffen.